videos, I talked a little bit about evidence from geology and earth sciences suggesting that the Earth is very old. Today I'd like to talk a little bit about some of the evidence from physics and astronomy that suggests that the universe is very old. We have to start with something that's very basic, very clear, very easy to understand, and really very serious. And that is this: starlight. According to modern physics, the speed of light, about 186,000 miles per second, is a constant. Light does not travel faster than that. It does not travel slower than that. Scientists don't think that there's any empirical grounds for believing that light has ever traveled at a different speed. And they think that there are very strong theoretical grounds for thinking that light will not travel at a different speed. At the same time, astronomers have over the past century and a half developed some very clever ways of estimating distances to stars and galaxies outside of our own realm. And the degree of accuracy or confidence that they have in these estimates decreases somewhat for things that are very, very far away, but they believe that they're in the right ballpark. So if, for example, they point the Hubble Space Telescope at a point in space and they just leave it there for a long time, take a long exposure, what shows up are galaxies in that space that appear to be very, very far away. And in fact, they believe that they are billions of light years away. Well, what does billions of light years mean? It means that, at least on the face of things, the light that we see has been traveling for billions of years. Light is emitted by stars. That light travels through space, and the distance it goes in 1 year is a light year. And billions of light years means that the light has been traveling for billions of years. Therefore, the universe appears to be very, very old. This, I think, is a very significant issue, and one that is very difficult for young Earth creationists to get around. There are more issues that come up in astronomy. One is that there are some places where astronomy and earth sciences seem to jibe in what they tell us about the age of certain things. Let me give you two examples of this. First of all, the Milankovitch cycles. There are cycles that have to do with the Earth's rotation on its axis or its revolution around the sun. And these cycles have very long periods. In one case, 23,000 years, in another case, 41,000 years, in another case, I think 100,000 years. What kind of cycles are we talking about? Well, for example, as the Earth spins on its axis, as you know, the axis is not completely perpendicular to the plane of the Earth's rotation around the sun. It's tilted. And the tilt then moves over a period of time. It's kind of like a top. When you spin a top on the floor, if it's not absolutely upright, it's going to begin to spin, and it's going to describe, the top of it's going to describe a circle as it moves around the floor. The Earth does the same thing. That's one of the cycles. Another cycle has to do, for example, with the eccentricity of Earth's orbit around the sun. As the Earth goes around the sun, it moves in an ellipse, not a circle, but there are times when the ellipse is more circular, and there are times when it's more flat. And it's possible from just purely astronomical data to figure out this kind of a cycle. And then there are other cycles of the same nature. These things take place over very long periods of time. Now, the interesting thing is this. Scientists who on Earth are using ice cores and sediments and fossils to try to determine something about the history of Earth's climate find correspondences in the data they are looking at with these Milankovitch cycles, which you would expect. Because if indeed these cycles have been going on for some time, the Earth is going to be receiving different amounts of energy from the sun at different points in the cycle, or the energy will be hitting the Earth in different ways, and so that should affect Earth's climate. So you would expect there to be some correlation between the Milankovitch cycles and past climatic change. And the scientists argue that there is. I am not in a position to defend these conclusions, but this is what most scientists believe. You can look this up online. Another example where astronomy seems to jibe with earth sciences has to do with the number of days in a year. Now, this one's interesting. As the Earth travels around the sun, it travels at a fixed speed. Well, not a fixed speed. That is to say, the length of time that it goes around the sun remains the same. So a year's length doesn't change over time appreciably because there's just not much out there in space to slow the Earth down as it moves. On the other hand, as the Earth spins on its axis, it is slowing down. How do we know that? We know it because of very good data on eclipses going back about 2,500 years. The Chinese especially kept some very good astronomical records. We have these records. We know when the eclipses occurred, and it's possible for astronomers to determine that over time the Earth's rotation is slowing. It's a very small slowing. It doesn't make any difference in your lifetime or mine, but it's appreciable. It's real. And the cause of this apparently has to do with the tides, or it has to do with the oceans and the Earth's pull upon the oceans. Precisely what the mechanism, I don't know, whether it's the sloshing of the water back and forth that creates friction and loses energy and loses angular momentum, or something else. I'm not sure, but it has something to do with the tides. In any event, the length of a day is getting longer. Because the Earth is spinning less and less rapidly. Now, if the length of a year remains the same, but the length of a day is changing, that would mean that if you project backwards into time, you would expect to find more than 365 days in a year. As a matter of fact, if you go back 400 million years to the Devonian period, you would expect a year to consist of about 400 to 410 days. And there is evidence that that is so. There are corals, there are shellfish fossils, there are sediments that show not only annual layers but also daily layers. And it appears that from that period of time, at that time, a year did consist of some 400 days rather than 365 days. In other words, we have here two cases, Milankovitch cycles, length of a year, length of a day, in which astronomical data and earthbound data appear to converge in telling us that the Earth is very, very old. Were the Earth not old, how could you have this kind of convergence? How can you explain this if there has not been time for the Milankovitch cycles to have an impact on Earth's climate, or if there has not been time for the slowing of Earth's rotation on its axis to make a difference in the length of a day? There are other issues, but let me just kind of go quickly to the question of how or what astronomers believe about the age of the Earth, and rather the Sun and the solar system. I mentioned before that using radiometric dating of moon rocks and meteorites, scientists believe that the solar system is about 4.5 billion years. I think it's 4.56 or something like that. Is there any way to test that? I'm aware of a couple of ways you can test it. First of all, it's possible to test this by measuring using instruments that can sort of use the Doppler effect to see what's taking place on the surface of the sun, measuring pressure waves in the sun. As you do this, you're getting an insight into what's going on in the sun. You then compare this with refined models of stellar evolution that tell us what a star like our sun should be doing at various points in its life. And you come up with the conclusion that this star, our sun, is approximately 4.5 billion years old. Another way of testing this has to do with what are called the missing nuclides. Now, nuclides are forms of elements. Some nuclides are radioactive, some are not. Some nuclides are being formed even today under Earth conditions. Some seem to be formed, at least according to scientists, only in the interiors of stars. Now, of the nuclides that are formed only in the interiors of stars, so they're not being formed now in the solar system, or within the part of the solar system we have contact with, the Earth and meteorites and the moon. Of these nuclides, there are 40 that are radioactive and have half-lives of less than 50 million years. Of these 40 radioactive nuclides, not a single one is found in the Earth's crust. On the other hand, there are 17 radioactive nuclides that have half-lives of more than 80 million years. All of these are found in the Earth's crust. What appears to have happened is that the nuclides have existed, but the ones with shorter half-lives have decayed. They no longer can be found. And given these dates, 50 million years, 80 million years, and the nature of radiometric decay, you can say that the Earth appears to be between 4 and 5 billion years old. So we have three main means of saying that the age of the Earth is approximately 4.5 billion years. What about the age of the Milky Way? I know of three methods of determining the age of the Milky Way, and to be honest with you, I don't understand them so well that I think I should try to really explain them. I'll just mention them to you. Scientists use globular cluster stars, which are believed to be the oldest stars in the galaxy, and they're able to determine from the amount of energy output from these stars how old they are. They believe this is a good gauge of the age of the galaxy. They make use of white dwarf stars, which also are special types of stars and behave in certain ways, and it's possible therefore to determine from the white dwarfs and the galaxy something about the age of the galaxy. They also make use of the abundance of thorium-232 and uranium-238 both of which are elements or nuclides that are created only by one particular type of nucleosynthetic process. So in essence, they're using radiometric dating also to date the galaxy itself. All three of these methods give answers or give dates for the galaxy of between 12 and 14 billion years. And the figure that's being used today, I think, is about 13.2 billion years. How about the age of the universe? Well, the universe can be dated in a couple of ways. First of all, there is the issue of the Hubble expansion. That is, the universe is expanding, and it's possible to measure that expansion. And it's possible, this is a gross oversimplification of what you do, but it's basically possible to kind of turn the clock backward and say, at what point did the universe begin to expand? If you do this, you get a date. This was true as of about 2004. I'm not sure whether this has been refined, of between 12 and 14 billion years. The other way of dating the universe, which I believe scientists consider to be significantly more accurate, is by making use of what's called background radiation. This is microwave radiation that is believed to be left over from the Big Bang. It's possible to measure this, and to measure it so accurately that it's possible for scientists to say, now that they believe that the universe is 13.78 billion years old or something like that. The figure has become more and more refined as time has gone on. So think about this for a moment. We've got three different ways of dating the solar system, and each of them is independent of the others. There's radiometric dating, there's pressure waves on the sun, there's the missing nuclides. We have three ways of dating the galaxy, and they're independent of one another: white dwarfs, globular clusters, prevalence of thorium and of uranium. We have two ways of dating the universe: the Hubble expansion, the background radiation. These are independent of one another and independent of all of the other forms of dating we've talked about. And yet all of these are consistent. All of these give a consistent picture of a universe that is billions of years old, a universe in which the Earth is not as old as the galaxy it is a part of, and the galaxy is not as old as a part of the universe that it is a part of. This is very, very substantial evidence from astronomy and from physics. And I don't think that I've scratched the surface of it. There's much more that could be said. Now put this together with what we've talked about before. We have evidence from sedimentary rock, from fossils, from igneous rock, from metamorphic rock, from ice cores, from sedimentary layers, and then all of this astronomical and physical data. To most scientists, I would say to all scientists who have not first been persuaded that the Bible requires them to believe that the universe is young, this evidence is completely persuasive. The universe is old. The Earth is old. Now, sometimes in young Earth circles, people speak as if the scientific community were right on the verge of giving all of that up and believing that, in fact, the universe is just 10,000 years old. I don't think that's true. I think that's very misleading. I think what has happened is that as science has progressed, the dating has become more and more precise. There have been changes, but the dates have tended now to converge. I mean, is the Earth 4.5, 4.56, 4.565 billion years old? That's the kind of place where there are questions in people's minds. No one is suggesting that the universe is young. And to the overwhelming majority of scientists, including, by the way, Christian scientists, including evangelical scientists, the evidence is simply beyond being overthrown. The universe, the Earth are very, very old. Well, okay then, if that's the case, what do the young Earth creationists say in response? I mean, how can they respond to this great mass of scientific data indicating that the Earth is old? How can they overthrow this, or how can they explain this? They have two methods that I'm aware of. The first one is young Earth science. We'll look at that next time. Thanks for watching.